Welcome everybody to the 14th episode of the Climate Seminar Series. And I'm Athanasios Nenes, and I'll be moderating the seminar today. It is our pleasure and honor to have two distinguished speakers invited today. The first speaker will be Professor Mario Paolone, who will provide a European perspective on climate change and its impact on power systems. Just a few words about Professor Paolone. He received his PhD degree in electrical engineering from the University of Bologna in Italy. And in 2005, he became an assistant professor in power systems with the University of Bologna. And he was there until 2011. And then since he joined EPFL, where he's full professor and chair of the Distributed Electrical Systems Laboratory here. His research interests focus on power systems, with particular reference to real-time monitoring and operational aspects, power system productions, dynamics, and transients. Dr. Paolone's most significant contributions are in the field of PMU-based situational awareness of active distribution networks, and in the field of exact, convex, and computationally efficient methods for optimal planning and operation of ADNs. Dr. Paolone is also the founding editor-in-chief of the Elsevier journal, Sustainable Energy, Grids, and Networks. So, Professor Paolone, when you're ready, please go ahead and share your screen. We'll be delighted to hear your presentation.
Excellent. So, first of all, Anastasios, thanks for the introduction. And let me also thank Climate for the invitation. It was really a pleasure for me to accept it. So in my time slot, I would like to focus on the impacts that the decarbonization of the power system is having and will have on the operational and planning aspects of the power system infrastructure. Well, this is a figure that is giving you the context of the global greenhouse emissions by sector. It's not really up to date, it's from 2016, but the figure of merit is pretty much the same. And the interesting aspect that you may see is that global greenhouse emissions are for 3/4 associated to energy conversion processes, which is this big red part of the pie chart. And this 3/4 part of this pie chart is almost split in 3 equal subparts, namely energy use in industry, transportation systems, and buildings. Now, this is telling you that the decarbonization processes have to change energy conversion processes in these 3 sectors to have a substantial impact on the global greenhouse emissions. Now, this is another figure that is pretty much known by people interested in this domain, which is the evolution and the breakdown of the global anthropogenic CO2 emissions until 2100. So this is now, and this is an horizon 80 years forward. Let's focus on the left part of this graph, where you see the annual CO2 emissions evolution associated to the electricity, which is this white part. So we expect to have a full decarbonization of the power grid somewhere around 2035, 2040. And in the colored parts, you have the CO2 emissions associated to building, transportation, and industry, essentially the 3 parts that I was describing before. Now, the majority of the decarbonization of these processes will be associated to their electrification, and therefore the decarbonization of the grid becomes even more important to decarbonize these other processes. That's why there is a lot of pressure in the decarbonization of the power grid that will have inevitable impacts on their planning and operational aspects. This is also reflected into the European Green Deal. Here I'm just focusing on 3 pillars that are associated to the 3 elements that I was saying before. If you read the documentation of the European Green Deal, essentially there is a pretty challenging target in the decarbonization of the transportation systems. It's clearly mentioned 55% of reduction of emissions from cars by 2030, 50% reduction emissions from vans by 2030, and essentially zero emissions from new cars by 2035. The second element, which is also associated to what I was saying before, is associated to buildings and in the impact that decarbonization may have. And the third one is about the cleaning of the whole EU energy system that is translated into a two-digit increase in new renewable energy for 2030. And again, in a range between 36 to 39% of new 2030 energy efficiency targets for final and primary energy consumption, which is pretty much matching with the three elements I was mentioning before. Now, which is a situation at the moment in the European Union? Well, the share of renewables in the power grid is quite scattered, and it's ranging between 5 to 54% as a function of the country. We have countries that are experiencing penetration levels of wind and solar power generation, which is larger than 20% of their overall annual electricity consumption, with some outliers, like Portugal, for instance, that has already experienced for a few days of the year a full supply of their electricity needs only from renewables, which is pretty remarkable. Now, which is the change in the paradigm of shifting from centralized power plants towards distributed generation? Well, essentially, there are two major, we have to separate the impact regarding transmission systems operators, essentially the utilities responsible for the planning and operation of the high voltage grid, which is also interconnecting the various power systems of the countries in Europe, and the distribution systems operators who are planning and operating the lower voltage part of the electrical infrastructure, which is interfacing loads and more stochastic renewables like wind and solar production power plants. Now, TSOs are essentially experiencing increased needs in what we call regulating power reserves. So essentially the amount of backup power that we have available at different time scales to compensate mismatches between production and consumption. I will talk about that in a moment. Whereas DSOs are facing significant issues associated to what we call grid reinforcement. So essentially the reinforcement of the assets, transmission lines, transformers, just to make a concrete example. So when you are increasing the amount of connected distributed generation, they're also facing quality issues of the supply and their dispatching capabilities. Essentially, their capability of following and tracking a power profile that is established a day ahead and that they are negotiating with the power. I will try to allocate some time in discussing how these two categories of challenges are nowadays addressed by TSOs and DSOs. So let's start with the first. So bulk power system reserves. So what I'm showing in this slide is the evolution of what we call imbalance netting. What is the imbalance netting? Netting essentially is a process which is agreed between transmission systems operators to essentially allocate the frequency restoration reserve. The frequency restoration reserve is an amount of reserve of backup power plants, let's say, which are in operation into the system and are capable to pick up the imbalance between what has been negotiated into the market versus what is currently realized in terms of power flows into the grid. Now, and the imbalance netting is established between different countries to avoid the simultaneous activation of this reserve in opposite direction. Now, this imbalance netting is a sort of proxy of the importance of the frequency restoration reserve that already introduced before along the years. So this is the increase of this imbalance netting from 22 2010 to 2020. So it went from basically 0 to something like 650 millions of euros per year. The colored part of this bar chart are associated to the various countries that are part of the ENTSO-E continental Europe power system. Now, this almost linear increase of the imbalance netting is telling you how much the needs of the frequency restoration reserve is increasing along the years, mainly due to the need of integrating stochastic renewables, essentially renewables over which we have a limited amount of control that requires the acquisition, let's say scheduling and deployment of adequate amount of reserve in order to keep the system in a balanced operation. Now, what we are talking about the balances, let's look at the top left figure. So what is showing this top left figure is the evolution of the frequency of a grid after an imbalance between production and consumption. So what is happening is that in the very first instances after there is an imbalance, the energy imbalance into the system is provided by what we call inertial response, which is the corresponding graph that you see on the bottom left. So essentially, the spinning masses that are into the power grid, let's say the big generation power plants, are slightly decreasing their speed in order to provide the power to the system and keep the system somehow in a sort of equilibrium. This inertial response will deplete very quickly and is replaced by what we call frequency containment reserve, which is an amount of reserve that is kicking in order to stop the frequency to decrease. And indeed, you can see on the top figure that after the imbalance taking place, the frequency stopped is negative derivative, thanks to the involvement of this frequency containment reserve. Then what is happening is that as time is passing, this frequency containment response is replaced by what we call secondary reserve and tertiary reserve, which are reserves that are acting at country level and a single power plant level for each specific country to bring back the frequency to 50 Hertz and recover the power imbalance that was triggered due to a certain event at T0. Now, you can imagine that this scheme, it's performing pretty much well if you have the full controllability of your power station. However, if you are displacing your power production in favor of renewables, you may lose significant control on stochastic renewables. Now, let's focus on the very first instances after there is an imbalance. So on the right figure, you can see the response of the system frequency when you're using what we call grid forming controls. So essentially, these are controls of distributed energy resources like photovoltaic panels or wind turbines that are imposing the voltage and they are behaving like a sort of synchronous machine. And this is, as you can see in the figure, helping to achieve lower frequency, let's say higher values of lower frequency after an imbalance and recovering the frequency equilibrium way faster than just using grid following control resources that we nowadays have to interface these resources. Furthermore, we have shown in a recent study that you can compress frequency containment and frequency restoration reserves at bulk system by dispatching local distribution systems. So essentially, if you equip local distribution systems with energy storage, for instance, you can day ahead dispatch your devices and you can avoid the need of having large-scale deployment and activation of frequency reserves at the transmission level. So this means that many of these controls and problems can be attenuated if we equip distribution systems with a sufficient amount of energy storage to enforce their dispatchability and then mitigate the power imbalances. So in a nutshell, for bulk system reserves, enhanced performance for the reserves assessment, provision of activation of reserves by taking into account power distribution systems is a must. It's something that transmission systems operators and grid codes need to take into account into the future. We can also consider active distribution networks into what we call defense plans in case we have black starts capabilities that have to be deployed. I will not talk about that because we don't have much time. Now, let's talk about distribution systems. So in distribution systems, as I said before, we have essentially two problems. The first one is network reinforcement. Network reinforcement is a change of the assets, so essentially in the thicker cables and larger transformers due to the presence of stochastic renewables. Now, the problem is that we don't have a model, a computer model of the whole distribution system of a given country. For the case of Switzerland, this is very simple because there are more than 500 distribution systems operators and they don't share their data. So what we did in my laboratory is to create a large-scale synthetic model for the whole power distribution grid of Switzerland. So essentially, we started from the knowledge of the extra high voltage locations of the substations, which are known. Then we create a Voronoi partition of these areas, starting from this location. We transform the heat demand into electricity demand. There is a very well established procedure to transform heat to electricity demand. We use heat demand as a proxy. And we redid a partitioning at the regional level to define the location of the secondary substations. And then we apply routing algorithms, which are typically used by distribution systems operators, to create a synthetic model for the whole distribution system, in this case of Switzerland, but this can be done for a whole country. So this picture is showing you the location of medium voltage substations, which are a synthetic model that together with the synthetic model of the whole distribution system of Switzerland is accessible open source on the GitHub that you see here. And you can also see the reference on the left. Now, what can we do with this kind of synthetic model? We can do many things. The very first one is that since we have an available model for the whole distribution system, we can compute what we call the hosting capacity of the system, taking into account the distribution potential constraints for PV generation, land use constraints, and the highly resolved PV capacity factors that can be embedded into the model. In these graphs that you see here, you can see the cost as a function of the installed power for various medium voltage grids that are into this synthetic model. You can see how the costs is not increasingly linearly. Why? Because at a certain point, when you are deflecting from a linear trend, the process is telling you in order to increase the hosting capacity of your system, you need to go into the direction of installing local storage. Otherwise, you have to reinforce the system. On the graphic on the left, you see the marginal cost for the same systems that are shown on the left as a function of the PV installed capacity in megawatt. And you can clearly see the discontinuity point in the marginal cost when there is the need of installing local storage to avoid grid reinforcement. Now, what we have also done with this model was to compute the hosting capacity for the Swiss distribution system. And on the top graph here on the right, you can see that we are hitting the hosting capacity somewhere between 13 to 14 gigawatt of installed capacity. After that value, you need to optimally locate battery energy storage systems. And here you can see the size in terms of energy and power. So on the left, you have the power sizing, the global power sizing, and on the right, the energy power sizing. Of course, you can also implement alternatives like demand side management, since they can have the same type of sizing in terms of power and energy. Again, I'm not discussing this in this intervention. Now, to sum up, the contribution of power distribution systems to the bulk power system frequency containment and restoration of reserves needs to be considered to counterbalance the constant increase of regulation services, which is associated to the massive connection of stochastic and non-controllable renewable power generation. So we have missed at the moment appropriate regulatory schemes and grid codes that are quantifying and properly remunerating these aspects into market mechanisms. There is a lot to do in order to further promote these aspects into the power systems operation. Second point is that the adequate and reliable day-ahead dispatch of active distribution networks that are hosting, stochastic, and controllable resources needs also to be better regulated, because its impact in compressing frequency containment restoration reserve is very large, and absorbing at distribution level stochasticity of renewables is one of the potential ways to go in order to maximize the hosting capacity at both distribution and transmission levels. Last point, planning strategies for the large deployment of stochastic renewables needs to take into account distribution grid's operational constraints. Not only Switzerland, but in general, in modern power systems, these are the bottlenecks that have to be solved. And this requires the fact of going beyond very usual reinforcement strategies, and for instance, hosting local energy storage systems together with the use of demand side management. So this is what I have to say to you today, and I'm ready to reply to your questions. Thank you.
And for the sake of time, we now need to transition to our second speaker, who is Christophe Ballif. Professor Balif is a director of the Photovoltaics and Thin Film Electronics Laboratory at EPFL and of the Sustainable Energy Center, and specializes in research and technology transfer along the value chain of both photovoltaic and energy systems. With his teams, he has contributed to numerous innovations, products, and startups in the field of photovoltaics, and collaborates with close to 40 companies in Switzerland and worldwide. His research and industrialization interests include materials and manufacturing processes for photovoltaics, high-efficiency crystalline and perovskite solar cells, module technology and reliability, specialty PV products for building integration or mobility, as well as all aspects linked to storage and management of energy systems. He is author or co-author of more than 600 scientific papers and of numerous patents. And in 2016, he received the prestigious Becquerel Award for his contribution to the field of photovoltaics, and he is an elected member of the Swiss Academy of Engineering Sciences. Whenever you're ready, Professor Ballif, please start. Thank you so much.
Thank you very much, Mr. Nenes. Can you see my slides?
Yes, very well.
Okay, so also thanks to Climact for inviting me, and thanks Mario for his excellent presentation before. So I will assume that Mario has solved most of the grid problem for my presentation, but of course, his work is of extreme importance. I'd like to step a little back and to give again a perspective on actually what we are experiencing now with this energy transition. And I refer to this graphic that is produced every year by BP in their wonderful statistics, and where you can see that in terms of primary energy, we still rely mostly on oil, natural gas, and coal. Nuclear has a very stable share. Hydroelectricity is slightly increasing, but not much. And what we've seen increasing is this share of new renewable, mostly wind, solar, and to a lesser extent, biomass. And so noticeably in this graphic, renewables are represented, multiplied by factor 2.5 approximately, because they consider that there is more values is equivalent thermal of producing this electricity. And we could have thought at the beginning of the COVID that things would improve, but as soon as COVID started to disappear, things are getting actually similarly bad. So, and the big question is, how do we get out of that? And I try to make for you a very simple calculation, knowing that it's still a long way to go. And by the way, this was photographed 1 month ago in the street in Switzerland, or make diesel great again now, a car from Freiburg. So we still have big issue to convince people of the importance of this energy transition. But if you have a look at the real numbers, the question is in terms of primary energy, in terms of producing energy, what should we do really? And if you have a look at this global growth of the curve for the primary energy supply, you can, in relatively quite confident way, assume that we need around 250,000 terawatt hour of primary energy in 2050, which is a factor 1,000 times what Switzerland or similar countries such as Austria need. And then you can start to make some assumptions saying, okay, I'm going to electrify a big part of my society with heat pumps, with electric car. I will need to keep some part for making power to gas and so on, and I will have some biomass. And then you come to the conclusion that mostly you will need to increase very massively the production of electricity to around 100,000 terawatt hours. So this is 250,000 terawatt hour divided by 2.5, which has to be compared to what we have today with hydro, 4,020 terawatt hour, nuclear, 2,600 terawatt hour, wind, solar, and globally we're around 25 to 27 terawatt hours of electricity production. And here you have basically four big solutions to address that problem, which can of course be combined. And the first solution is to say, okay, I will put a lot of solar and a lot of wind. And of course I will still have hydro and biomass, but basically you would need around 40 terawatts, or 40,000 times 1 gigawatt of solar and 15 terawatt of wind. You can change, of course, the ratio. Then you can also say, I would like to cover that with nuclear. So you'll need roughly 11,000 big nuclear power plants, or 100,000 small nuclear reactor, which would very quickly deplete completely the uranium reserve. And even in the best scenario of the nuclear industry, there might be a doubling of the nuclear energy production by 2050, but certainly not a multiplication by a factor 25. Of course, you have the possibility to sequestrate carbon, but it's a lengthy, long process and not much has happened at industrial scale so far. And finally, you could say, I don't care, or it is too late. So this is what we call now the climate pessimistic. So they said for a long time, we cannot do anything. And now they say it's too late. So certainly what will happen will be a mixture of all this. And when we come, of course, to the first scenario with the massive implementation of wind and solar, there are a few questions raising. First, do you have enough energy? Can you do it physically? What is the impact on sustainability? And so on. I'd like to start just by citing one paper, which I like a lot, because this is a paper that takes into account the learning curve and the progress that we make with wind, solar, and with battery by the group of Christian Breyer. So it is not a power system guy. He's more looking at the quantity of production, but he has tried to simulate hour by hour in the case of middle penetration or change to renewable energy in the European grid. And he has made even the assumption that there is no more fossil fuel and even no more nuclear, and he's replacing everything with wind, with photovoltaics, and with biomass and waste. And interestingly, what we find in his paper, and this is the kind of base scenario that, as Mario mentioned, could apply to many parts of the world, is that with a good complementarity of wind and solar at European level, you could have a system that works. You have a few adaptations to make to the grid, but they are not enormous because you will anyway need to rely a lot on storage. And in his scenario, he works with pumped hydro storage, which is the green part. And he works then massively with electrochemical batteries, which are also doing big improvement in their pricing and cost. And interestingly, in his scenario, he found that we could have electricity on the mass market for the same price as before, without even speaking about the current increase in the price of coal and gas, but in a sustainable way. So this kind of scenario have been developed by many groups. You can see a scenario where you have a full decarbonization by Solar Power Europe or by the European wind platform. So they come with completely different conclusions on the quantity that you need. But basically this kind of scenario is what is guiding a lot of the policies and partly of the research in the field of renewable. And with taking this scenario seriously, well, I have to say, you can have a look on this graphic. This is what has been done in terms of new capacity for renewable energy. And these are here just the announcement for China. And only 1.5 months ago, China announced that they would install 570 additional gigawatts in the coming 4 years through their 5-year plan. And actually, China is one of the countries, even though they still build a lot of coal power plants, that is taking this very seriously. Germany has announced quite ambitious plan to put much more wind and solar, and many other countries are actually lagging in what should be done with respect to developing massively this source of electricity. And now I just allow myself to give a kind of global vision, and I hope you can share with that with what certainly should happen. And certainly the best is to develop anyway massively wind and solar, and of course all other second order sources, because they do not have the same potential. It is biomass, it is hydro and geothermal, and of course capitalize on the existing hydro, especially in Switzerland. We should not throw away our fossil fuel assets. We should keep that for flexibility. I mean, in Europe, we have, I think, almost 200 gigawatt of gas power plants. They should not run 100% of the time, so they should run at a low capacity factor. And certainly, it's not a good idea to kick out nuclear too quickly. We need to facilitate this transition to still use and maintain properly the nuclear assets. You need, of course, to capitalize on this huge improvement that have been triggered by electric mobility on electrochemical storage, and can be part of the solution. And of course, also develop power to gas, which is starting to develop. There are big projects now, especially for decarbonizing the industrial sectors that needs chemicals, that needs heat. And you can see in Spain, for instance, now you have the first multi-gigawatt solar plus hydrogen that will power industrial sites that are ongoing. And of course, in order to manage all that, we need Mario and his teams, but many more teams to work on integrating all that into an efficient system. Then, of course, you have everything related to energy efficiency, which have been a little forgotten, but we need absolutely to also improve a lot of our houses and to track losses of everything. Just as a reminder, in Switzerland, there are several terawatt hours, if not almost 10 terawatt hours of electricity that is been wasted in inefficient pumps, ventilation systems that are running all night long, and so on. So a lot can be done here. Ideally, if we would live in a world where people really think, we should also think of sufficiency, sobriety in French, rethink our consumption, and also accept that there might be critical period in the year where, for instance, we should maybe renounce to some of our comfort, and of course, we think globally of a way of consuming, of burning energy, and of buying things. But this is something that's very difficult to address, but we see more and more people taking personal initiative in that field. Of course, you can do a lot with agriculture. We've seen on Mario's graphic, agriculture is responsible for a lot of the emissions, so you should tackle that. And of course, also use soil, lands, and biomass to sequestrate carbon, which is the cheapest way so far to do so. And finally, there is a big element of strategy. We've seen that with the war in Ukraine, that we don't want to be absolutely dependent on other countries, especially other parts of the world with very, say, dictatorial government, which can decide to cut supply or cut production of something that is useful for Europe. So we should think of also developing an industry for our energy infrastructure and assets. We should think about resources. It looks like Europe has been one of the only places of the world where we do not think about how are we going to supply ourselves with metal, with lithium, and so on. And we need to think about manpower. We need a lot of people to make this energy transition. And especially now we see in Switzerland, there is a lack of manpower, and which can be addressed in different ways. But one of the installers in Switzerland told me, you have to pay people well, and people will change the job and will join this industry that needs a lot of people to renovate the houses, to install solar panel, heat pumps, and more. So with that general introduction, the question is, what can photovoltaics do in that, and does it make sense? So photovoltaic, as you've seen, can a lot, but of course it is fluctuating, it is predictable, but sometimes you have less, you have no at night, it's obvious, and you have less in winter. One good thing about photovoltaic is that it can be curtailed. That means it can be, you can simply, through the power electronics of your inverter, you can tell the system not to inject its energy. So this makes me say that you have never too much photovoltaics. You always have an easy way to curtail it. And the major question are about the price, the cost, the volume, and the sustainability. So as you all know, this curve is very famous. It is a curve that shows that the price of PV panels has gone down by a factor almost 30 in 30 years. Coming down in 2021 to module price, sometimes even below 20 cents per watt, meaning $40 per square meter. Now the prices have gone up again. There is a lot of demand. We have a lot of problem with the shipping, especially many products come from Asia, but these bottlenecks are no fundamental bottlenecks. in a cumulated way, there have been now in April 2022, 1 terawatt of photovoltaic already installed, which is amazing, considering how young somehow the market deployment has started. And also in terms of pricing, it's interesting to see, even if you import a solar module, you can make the calculation. It's going to cost for basic module 60 euro, and it's going to produce between 60,000 and 9,000 kilowatt hour over its lifetime. And if you make the comparison with importing 1 liter of oil, and before the Ukraine crisis, you see that in terms of useful energy, it's a factor 15 to 20 times better. So it's much cheaper to import a solar module that makes electricity and run a heat pump or an electric car than buying oil or heating oil in a very impressive way. This being said, if you had this strong decrease in the price of solar module, people have also improved the way they install solar parks. Now it's come installed on one axis tracking system in most of the parks. The modules are bifacial to recollect part of the light that comes from the ground. And this allows basically a strong decrease in the final levelized cost of electricity for wind and for solar, but also for wind. And you can see on this graphic, which is a collection of the typical LCOE for solar power plant, that it goes from around 2 cents per kilowatt hour up in average to 5.7 cents per kilowatt hour for solar electricity. So these are for large parks. And at the same time, you had huge improvement in the onshore wind and in the offshore wind. And now basically you are at the same level as fossil fuel power plants, assuming a low cost of the fossil fuel. And in many cases, now you can be significantly below. And of course, this happened just in 10 years. And as you know, policies have sometimes problems to see how fast technology is evolving. And here, certainly, we had a complete revolution in what happened. And this explains now why you can have this very low cost electricity. And this explains also why when you start to think of large scale projects in the south of Europe, even for making hydrogen, you will be able to generate electricity at something like 1.3 cents per kilowatt hours in 2030. And this allows very clearly to make hydrogen or to make ammonia gases and to liquefy it and to also offer solution with power to X. Now you could ask yourself, okay, we need to maybe put 40 terawatt of photovoltaics, so we need to install 40 times more photovoltaics. What does it mean practically? Well, it means that we should increase the production volume of solar panel on globally to a volume of around 1 to 2 terawatt of module per year, coming from around 4.15 terawatt per year today. And you might wonder how much it costs, and you can have a look at this nice paper that sees that just all the production system, it means going from refining the quartz to making polysilicon, to making solar cells, to making solar modules, the investment would be in the range of 18 billion per year. 18 billion, which is actually at the scale of our problem, really nothing. So the investment cost for producing a lot of module is not an issue. And of course, the good point is because we are doing research and development, that means also that the market should grow and there will be a lot more of innovation to come. Now we can start to think about the sustainability of making these solar modules. And here I just would like to show you a few recent elements of what happened in this field of photovoltaics. The first thing, and you can find a very nice review we just published about crystalline silicon photovoltaics, which will remain the workhorse of the industry for the coming decade. You can see here the average efficiency of the average solar panel, which was in the range of 14% in 2006. Today, almost any module will have an efficiency of 20%, and some improved technology can be at even 22%. And this evolution is dictated both by improvement in some technologies and by changes in technologies. So this would be a full lecture to explain you everything that happens on this market. But basically the message is that there have been an increase of around 0.4% of the absolute efficiency of module every year per year. In 2030, you will find 23 to 24% module. Perhaps if we are able to bring perovskite on silicon, you might even go higher. And for your information, of course, in the Châtel, we work on various kinds of technologies, and we are always trying to target to be above this curve so that there is an interest from industry to bring this to the market. And this brings us to the point that basically by improving the efficiency, by improving a lot of the manufacturing process in the polysilicon, in the cutting of the wafer, we've been able to reduce by almost 6 the quantity of silicon used in the solar panels. It costs much less energy to make these panels. And now the good news is that first, in terms of energy payback time, we are almost everywhere, even in Switzerland and in the other part of Europe, we are at around 1 year for the energy payback time. With less than around 0.5 to 0.6 kilowatt hour per watt of module to make 1 watt of module. So this is very attractive, and it means even if the electricity price go up, you can still manufacture solar cells and module with a limited cost. And also, and I'll be very quick on that, if you have a look at the carbon emission during the manufacture of the photovoltaic module, it depends very much on whether you made that in China with coal power plants or partly in Europe for the polysilicon and other part of the process, but we're talking about 20 to, in the worst case, with Chinese modules made with coal, about 40 grams of CO2 per kilowatt hour, which you can compare to what is emitted by gas power plant or coal power plant. And if you have a look at that, and if I take good practice now with 200 grams of CO2 emitted per watt of module, it means that if we want to make 40 terawatt of modules, we would need around, you make 300 grams times 40 terawatt, and you find that it would be around 12 gigaton of CO2, which has to be compared to what is remaining in the scenario at 2 degrees. So we should keep a very small share, which is less than 1% to make our photovoltaic modules, and keep roughly the similar share to make the wind turbines and to make the batteries, knowing that when we improve the system, then it becomes cleaner in terms of energy supply, then all these numbers go down. So it is possible, but of course there is an impact. Okay, now what we do, of course, we try on the strategic side to reindustrialize Europe to also bring part of the module. And for instance, we work a lot with the group Meyer Burger. They have now installed the only new production lines for solar cells and module in Europe. They are going to 1.4 gigawatt of annual production capacity. They target 7 gigawatt in the coming years. And here we see that European customers are really ready, at least for their roof, to pay more because they don't want to be, let's say, associated to perhaps controversial human rights practice as happened in some part of the world. And this brings me to invite all people to try to work when they can with European products. And to finish a little more on a Swiss note, and there are a lot of things you can do with solar. Do we have enough space in Switzerland? Of course, we have a lot of space, so you can think of crazy projects. People have proposed to cover highways with photovoltaics. We have a lot of potential on our building, up to producing 50 terawatt hours. We have on our facade up to 17 terawatt hours of facade. It's not 50 kilowatt hours, 17 terawatt hours. And we have much more if we consider all these unconventional surface parking lots along the railway and so on. And you have very innovative companies such as this one here. They are making deployable stations that you can put on top of sewage station. So you really have the possibility to cover a big part of your electricity and energy need with photovoltaics. And actually it is a factor 50 times more efficient than biomass. So you don't have enough space for biomass, but you have enough space with photovoltaic. And you have the buildings. And of course, Switzerland is a country with a nice, let's say, a cultural heritage. And you would like to do as much as possible first on houses, and then maybe you go to other places. And we should avoid in Switzerland to cover only a small fraction of the roof and a small part of the roof because still our roof spacing is limited. And this is why Switzerland has developed a lot of innovative solutions. We don't want to see photovoltaics like on the left side, like here, we rather want to see it discrete. And this explains why we have many companies developing what I call this nice integrated solution so that every building can start to become a powerhouse. You can see here a kind of traditional mega slate products installed over 14,000 times in Switzerland. So this works very well. This is black, so you can do wonderful things. You can even make some niche products, such as here. You know, the small systems make the big energy in the end. A few years ago, we developed the first white photovoltaic modules. It has been a long time for the development, but now we see, after trying to sell that at some US president who was not very much caring for global warming, we continued the development, and now you can start really to see the first white photovoltaic buildings. It means you're no more limited to making energy on your roof. You can put that on the facade, and you don't want to have only black facades, and we see more and more of these projects. So in some of the other developments, you can see here also these terracotta colors that can really be used in places where usually regulation do not authorize standard PV modules. And we see also more and more customers going for such project, private people. These are wine caves in Neuchâtel. Here, this is a new building in Zurich, or an old building that has been refurbished with Solar Access and Trias modules, which are also made here, in that case, in Switzerland. So there are really no limitation in what you can do. And if you really like photovoltaics, you can do it like here. You can see these are small photovoltaic tiles. You even have photovoltaic on the edges of the roof. So this is a little crazy here, and it costs quite a lot of money, but I have to admit, this is my roof. Huh? And you can do a lot of things with these nice solar tiles. I show you here a few amazing projects. And if you really like photovoltaic arts, you can also even make photographic picture. And we start to see private people installing this kind of PV panels in their garden. And they're going to make a few hundred kilowatt hours with such a system, covering a part of their production with the art in addition. So with that, I hope I could show you that photovoltaic will be an important part of this energy transition. It will be a huge challenge to make it cost effective. People are ready, however, to pay more in some cases. There has been huge improvement in the sustainability aspect of photovoltaics. You can curtail it, so there is never enough. And certainly we also see that a pure free market, that is another discussion, will not be enough to manage completely the European network. So we also need rules and regulation to continue promote this development of renewable, but also to put in place the right tools for controlling and managing the system at large scale. And finally, of course, local manufacturing for all these critical components for our energy transition are important. So we should really think about this local manufacturing. With that, I'm finished, and I thank you for your attention.